Thank you very much. I'm very glad to have Professor Evgeny Shinder as a speaker of this colloquium. And Professor Evgeny Shinder got his PhD under Professor Surin at Northwestern University, and he is now full professor in Sheffield University in England, and also as a guest professor of our University of Tokyo until end of the June. And Professor Shinder has studied algebraic geometry, in particular scope of very high originality, especially in derived category and Grothendieck rings of varieties, and they are very impressive application for hyperkähler manifold, Lagrangian fibrations, and birational geometry, rationality, and Cremona groups, and so on. And actually he got the London Mathematical Society Whitehead Prize last year. And today, he tells us Gromov cancellation question in birational algebraic geometry. So please start.
Thank you very much. Thank you for the invitation to speak in this colloquium. I'll talk about some of my recent work on Gromov cancellation question. So to begin with, I'll say some words about what kind of questions we study in algebraic geometry, and then I'll explain the Gromov question and some theorems regarding it. So very roughly speaking, in algebraic geometry, we study the birational category of algebraic varieties. So you take your favorite field, complex numbers is the simplest, and then study the category of, birational category over K, consisting of objects algebraic varieties over K, so given by algebraic equations, and morphisms are birational maps. So birational map is something specific to algebraic geometry, which doesn't really live in other domains very much. So it means that we have a big open subset, dense open subset in X, on which the morphism is well defined and gives an isomorphism to the corresponding subset on the other side. So basically, varieties are birational when there are dense open subsets in X and Y respectively, and an isomorphism between them. And then the morphism may not be defined on the complement. Right, so yeah, that's the category, and birationality of varieties is one important question one wants to study. Specifically, the very rough goal of algebraic geometry is classification or birational classification of algebraic varieties. In particular, one wants to know about rationality, namely, when is X a rational variety, which means birational to the flat projective space Pn. So one wants to know both constructions and abstractions for this kind of questions. And in terms of morphisms, one would ask about how to describe the birational automorphism group of a variety. So it includes all the actual regular automorphism, and sometimes it just coincides with the regular automorphisms, but sometimes, like for a projective space, it's a lot bigger than the regular automorphism. It becomes a very interesting group. So the specific question here is to understand the very big Cremona group, which is the group of birational self-maps of a projective space over your field. Yeah, so this is kind of the basic domain where we're working. Objects are algebraic varieties and morphisms are birational isomorphisms. So let me introduce the question I want to focus on in this talk, which is something Gromov asked quite some time ago. The question goes as follows. So you have two algebraic varieties, X and Y, and you embed them differently in the same variety W. So that's the picture. So you have the same variety W, and there are some two differently looking varieties X and Y inside that W. And the assumption is that the complements of X and W and of Y and W are the same, isomorphic. So in other words, in terms of what I said on the previous slide, I have a birational map from W to W, which is an isomorphism over this blue complement to my closed subvarieties and does something else which we don't know what over X and Y. So I deliberately drew X and Y a bit differently, and one of them is a bit singular here. Then the question is, what about X and Y themselves? Namely, in typical examples, when this happens, the map that you have extends to X and Y somehow and sort of tries to identify X and Y with each other. So that's the typical behavior, and the question was, are X and Y themselves birationally equivalent? Even though in general, they don't have to be birationally equivalent through this map. So maybe the original map contracts X and the inverse contracts Y, but sometimes X and Y are still birationally equivalent. And more precise version of the question is, in this situation, once the ambient varieties are the same and the complements are the same, it's tempting to think that actually X and Y are so-called piecewise isomorphic, so built up from the same pieces. So specifically this means that there's a stratification of X into locally closed subsets and of Y into locally closed subsets, such that after permutation you can match up the pieces. So maybe this singular point can be removed here, some point can be removed here, but eventually all varieties are matching up after this cut and paste regluing. Yeah, so that's the question which Gromov asked in 1999, and back then all the possible answers were positive. So there were just examples when, for one reason or another, X and Y actually were isomorphic or birational. Yeah, so that's the question, the Gromov cancellation question, and kind of I want to develop some techniques and language to show when the answer can be negative and when the answer can be positive. So various devices to measure what happens. The first thing I want to explain though about this is that it's too much to hope that X and Y are actually isomorphic. So maybe the most naive question would be to say, okay, if the complements are isomorphic, then are X and Y isomorphic? And to this, one can easily make an easy counterexample. So I'll write some equations now. I said algebraic geometry, we do geometry of algebraic equations, and there will be mostly no equations in this talk, apart from this slide where actually I do have some explicit curves. So I want to show you a basic example of how complements can be the same, but closed subvarieties can be different. So I have my ambient space is C2, so a complex variety, smooth, not projective, and I have two curves, X and Y in this C2. So they're reducible, but it doesn't really matter. One can make similar examples with irreducible curves. So basically, how does this curve look like? So both of them is a union of the coordinate axis y equals 0 and this curve here, or coordinate axis y and this curve here. One thing which is easy to see is that these curves are not isomorphic. Specifically, both curves consist of two components, but the first one is connected, so this component intersects this component, and the second one is disconnected. When y is equal to 0, this has no solutions. So as algebraic varieties, they cannot be isomorphic. However, it's very easy to see with basically the equation of the blow-up here. As soon as you remove big X and big Y from C2, then the complements are matching up perfectly. So as soon as you remove this coordinate axis and you allow yourself to divide by Y, the other two curves match up perfectly. So that's kind of the nature of the question, that complements are isomorphic, the curves are somewhat similar, but a little bit different. So this is the expected behavior in the Gromov's cancellation question. Specifically, here the answer to the stronger form is positive. So if I start, so there's some problematic point, 0, 0, and if I remove this point from both curves, then this very same equation gives piecewise isomorphism. So I can stratify my curves into pieces and then arrange the pieces to match up perfectly. So this is an illustration how we shouldn't really hope for an isomorphism, but piecewise isomorphism is quite reasonable thing to expect and to hope for. Now I want to set up some language to where we can start measuring situations like this. And so it's called the logarithmic ring of varieties. It's one of the standard techniques in algebraic geometry. It's kind of a formal ring which contains all algebraic varieties, and we can do manipulations in this ring to learn about properties of varieties. So generators are isomorphism classes of varieties X over your field. You can look at quasi-projective varieties or all varieties. The answer will be the same because of the relations. The relations are called scissor congruences or cut and paste relations. For every open subvariety with a closed complement, you declare this relation that X is equal to closed subvariety plus the open complement. So you make this kind of big universal object containing all isomorphism classes of algebraic varieties over your field. And I'll explain some properties and why this is relevant. So that was an abelian group, and the product structure is induced by the product of varieties over K. So it naturally becomes a ring, and this ring 1 is the class of a point, because multiplying by a point doesn't change the isomorphism class of the variety, and there's a very important class of the affine line called the Lefschetz class. So what's the immediate relation to the Gromov cancellation question? It's as follows. So like if you remember the statement of the question, it was X and Y were embedded into W and complements were isomorphic. And just comparing the relations for the two sides in this ring, we get that formally equality, like isomorphism of this open complements, means that their classes are equal in the ring. And this means that by doing the algebra, that X and Y have the same class. So kind of the question is asking, okay, you have the same class in this ring. What does it mean geometrically? And kind of the naive expectation is that, okay, so it looks like what you're supposed to do is, okay, equality should imply that maybe you are made from the same pieces. This was the understanding at the time. In the example with reducible curves above, indeed, the two classes of the curves were the same, and if you stratify them as I prescribed, you get 2 times the class of the affine line minus the 1. So far so good, everything matches, and there are no interesting phenomena yet. In principle, to get positive answers to the Gromov question, the starting point would be, if you have an equality like this, then what can you say about X and Y? What do they have in common? But this is not so easy. I'll say some words now about how this ring appears. So this ring appeared in the Grothendieck-Serre correspondence as the first version of the ring of motives. So when, namely, it has a certain obvious universal property, specifically certain invariants just factor through that ring. So let's say you have an invariant mu of algebraic varieties which take values in a commutative ring R, and satisfying the properties like in the definition of the Grothendieck ring, namely, for every closed subvariety with open complement x minus z, your invariant is additive for this kind of cut and paste decompositions. And secondly, it's multiplicative for the product. So let's say you have such invariant. I'll give examples in a second. Then just by definition, you can define this, you can factor it through the Grothendieck ring and define it to take the class to the corresponding mu of x, and the relations are preserved by this and by this. Yeah, so every such invariant factors through uniquely. So in some sense, yeah, this is the kind of, it's a universal invariant with this property. And so examples are maybe familiar. There are topological examples, such as like topological Euler characteristic with compact supports. You can understand it as if your field is complex numbers, or otherwise you can do étale Euler characteristic over the field of your choice, and you also get an integer satisfying these properties. The second thing is, if you're over a finite field, you can do something totally different and start counting points over your field. You get finitely many solutions in finite fields, and then you get homomorphism like this, two integers again by counting points, which satisfies obviously both properties. And finally, much less trivially, over complex numbers, Hodge numbers, when you put them into a polynomial, into variables, also gives you such a homomorphism. So this, for example, this follows from Delign's theory of mixed Hodge structures, that we get such an invariant. Yeah, and traditionally, like since Grothendieck times, things which unite properties like this are called motivic. So an old meaning of the word motivic invariant or motivic abstraction is referring to this ring. Nowadays, there are more sophisticated version of categories of motives, but this is kind of, those things are typically called motivics, which satisfy these properties, which lift this some more universal ground. So, so this is the general philosophy about this Grothendieck ring or ring of motives. Now let's think a little bit about what do we know and what do we not quite know about this ring. So it looks very attractive in the sense that it looks easy and it carries a lot of information about algebraic varieties. Like one thing which is true indeed is that certain computations are nice and simple. Specifically, if you have a projective bundle or a blow-up, you can cut and paste and write relations between the source and the target. So for example, for projective bundle, you get something similar to projective bundle formula in cohomology, Chow groups, or other motivic theories. You simply have to take the class of the projective space, which is this geometric series in the class of the affine line, and times the base. And the proof is very easy. You just look at an open subset where your projective bundle is locally trivial. This is true, and then do induction on the dimension of the base. And there's a similar formula for a blow-up, which also matches blow-up formulas in cohomology and Chow groups. So in the geometric situations, it's easy to write down relationship between the objects involved. However, in many aspects, it's not a very nice ring. It's non-Noetherian, very big, has zero divisors, which are not understood. Equality is not really understood. And in particular, the class of L itself kind of counterintuitively happens to be a zero divisor. So there's kind of something going on there. So why it is surprising is that in usual motivic theories, L is a Tate motive, so tensoring with it usually gives you an isomorphism. You're not supposed to have any kernel. But importantly, this ring does have annihilator of L, and there's some interesting information contained there as well, which is not fully understood. The strongest structural thing we know about the Grothendieck ring is Larsen-Lund's theorem about the quotient of the Grothendieck ring by annihilator of L. Specifically, it happens to be a free ring on stable birational classes of varieties. So, and it's very important because once you have an equality of classes, then you can factor them through here and at least deduce that your varieties are stably birational, have something in common. But this is one of the rare structural results known about the ring. Yeah, so as I mentioned briefly already, so this structural result, which says that it's a free abelian group on something, on some classes, implies that equality of smooth projective varieties doesn't tell you that varieties are made of the same pieces, but at least they are stably birational, which means that if you multiply them by projective spaces of some dimensions, they become birational. So you get some kind of control from the equality of classes to geometry, even though not very strong control. And so using this, one can get some interesting applications to birational geometry. So let me mention two of the highlights which include my work. So the first thing is that, okay, I mentioned that L is a zero divisor, and this was, so with Galkin we have some work about cubic fourfolds, and if annihilator of L was trivial or one can reformulate it if we knew certain things about this annihilator, that this would be generated by some relations of specific kind. We would get control of irrationality of cubic fourfolds. This used Larson-Lund's theorem among other things. And another thing is that because of this relation to stable birationality, one can show that certain properties such as rationality and stable rationality are specializing in smooth families. If you have families which are smooth or mildly singular and general members were birational, then the limiting members are also birational. This is a formal consequence of certain specialization map for the Grothendieck ring. So indeed, the ring is complicated, but one still gets some benefits from it. So, but however, one of the kind of key questions is, if you have a quality of smooth projective varieties, what does it really imply? And it's not very clear, basically, and much of what's coming now in the talk is about that. I want to refine my structure a little bit. So I define Grothendieck ring of varieties as certain free abelian group modular relations. And I want to make a more refined structure, and then I'll explain why I do that. Specifically, I want to bound dimensions of my varieties. It doesn't seem to make much sense at first, but it makes a difference. Specifically, I look at generators, which are not all varieties, but only varieties with bounded dimension up to n, where n is a natural number. And I put the same relations, cut and paste relations as before, but just for varieties that I allow now. And of course, I have connecting homomorphisms between different levels of my truncated Grothendieck groups, because I can consider n-dimensional varieties as n+1 as dimension up to n+1, and relations here are also remaining relations here. However, the subtle thing is that these maps are not, we don't claim they are injective. So specifically, even though the Grothendieck ring is the colimit of all these guys, just by definition, every variety has some dimension, so it comes from one of the terms here, and every relation comes from one of the terms here. However, it's not quite the union. That's what I want to say. Namely, we should allow ourselves thinking that these maps have kernels. Right, so negative answer to the question that I'm addressing will have to do with these maps being non-injective. So you start going from one level to the next and you lose something. So how would it feel? It would feel as follows, that you have some n-dimensional cells which maybe don't talk to each other, but if you start adding n+1 dimensional cells, you get more relations. Right, so you should remember the original picture from the Gromov cancellation, and kind of if the question has a negative answer, it would be having to do with differences of classes here being non-zero, but going to a class which is zero here, right? So this is the logic of the situation, that the maps don't have to be injective, and their non-injectivity is about that question, and we'll be making this more and more precise. Yeah, that's something quite non-intuitive. So yeah, maybe 20 years ago, there were conjectures about all this being injective, and so, yeah, people thought that it was simpler than this. Yeah, and so I want to look more precisely at this potential failure of injectivity. So I haven't made any examples yet, but I want to just define nth Gromov subgroup to be this kernel of the connecting map from K0 varieties up to n to K0 varieties up to n+1. Yeah, so I make this definition, and then I will want to study this group differently. Yes, and G stands for Gromov subgroup. Right, so kind of by definition, I can start writing exact sequences like this. So I have my connecting map here. Going from n-1 to n. This is the kernel. By definition, it's Gn-1, n-1 Gromov subgroup. And then I want to look at the co-kernel. So what stands after, so what is the quotient of this by the image here? This actually is easy to figure out. So the kernel we don't know yet. Maybe it is there, maybe it is not there. When it is there, it will be hard to describe. But this quotient is easy to describe. Specifically, what happens is as follows. So you look at all your varieties of dimension up to n, and then just quotient everyone who has dimension n-1 or smaller. Like you declare that all the pieces of smaller dimension don't matter. And so the relations become trivial. The Grothendieck group relation, which was x equals u plus z, just becomes x equals u, because z is now gone, right? And eventually we get a free abelian group on an equivalence relation, which is called birationality, right? Because, yes, once again, if I impose these relations here on top of saying that everyone of smaller dimension is 0, the resulting relations will simply look like x equals u for every open subset. But x equals u for every open subset is exactly birationality relation, because you always have a common open subset. So you end up with a free abelian group on birational isomorphism types. Yeah, just by definition. Right, so interestingly, this quotient is a free abelian group. This is not clear, and then we have the sequence. So it should be surprising this is free, because, for example, it's not known whether these groups are free or torsion-free or not. They definitely look like they are kind of free on something, but it's far from obvious and possibly false. So, as I'm saying, existence of torsion here is not known, even though it's not predicted anyway by the definition, it's not known either. So it's kind of a relevant, interesting fact that this is a free abelian group, actually. One thing which is easy to see is, and kind of it shows how birational geometry comes in here. So let's look at the 0th group, right? So the 0th group is when we go from 0-dimensional varieties to curves. And kind of, it's a question about compactifying open curves and whether this compactifying open curves gives us unique boundary or not. So on the level 0, we are looking at punctured curves and counting points at the boundary, kind of, at least over closed field. And because of uniqueness of models in dimension 1, this map actually has a splitting, right? So kind of how would such a map be injective? For example, if I could produce a splitting, and the splitting is produced by looking at the boundary at infinity, which is well defined in dimension 1. Yeah, I'm kind of saying complicated words here, but actually it's an easy statement that for curves, everything is unique and there will be no kernel. But this is the only easy statement about these groups. So I'll get some vanishing and non-vanishing results, and they will be more complicated. Yeah, so I want to now slowly move into this counterexamples, non-vanishings, and abstractions. Right, so before that, let's look at the G1. So it's when we glue curves to surfaces. We go from dimension 1 to dimension 2. And here, this is still 0, but here already have something. So could be algebraically closed field or homogeneously perfect field. So it's already a non-trivial result just because it uses, there's some assumption on the field. Otherwise, we don't know. I don't say much about this proof, but basically it uses minimal model program for surfaces and link factorization for surfaces to check that there will be no abstractions there. And this is an easy theorem over an algebraically closed field, and it takes a lot more effort over more general perfect fields. But as a positive things, some consequence of this vanishings, namely for G0 and G1, we get that if we look at surfaces and below, everything cancels perfectly. So when you start embedding curves into surfaces and ask about whether complements, closed complements match, this vanishing tells you that everything that as soon as your complements are the same, your curves were equivalent already on the level they live. Specifically, it meant that they were up to stratification the same as curves. So it was a very strong positive answer for ambient varieties of dimension up to 2, as in the example I gave at the beginning. And another consequence is this. So I said that the quotient each time is this free abelian group. So level 2 modulo level 1 is this free abelian group, level 1 mod level 0 was this, and finally this is level 0. And in this dimension, Gromov subgroups G0 and G1 are vanishing, so the sequence is split just because the last term is a free abelian group. The sequence is split. So in particular, I get this structure, and in this case, it follows that they are free, and in particular torsion free, something which we don't know for higher levels. Yeah, so basically, as soon as we get some vanishing, then we get very good control over the Grothendieck ring and of this Gromov cancellation. But the more interesting thing is non-vanishing and how these groups are non-zero, the splittings fail, and cancellation fails. Yeah, so this is one of the way to state the main result. I'll later restate it a bit differently. Right, but yeah, in these terms, Gromov subgroups are non-zero for the following cases, and now I list some dimensions and some fields. But basically, like if I simplify, in all other cases, it's kind of zero. So specifically, you can go from surfaces to threefolds over some small fields, such as number fields or function fields, and later on I'll explain why these fields and not complex numbers, say. Now, yeah, we can go from threefolds and higher for any field of characteristic 0, and finally fourfolds and higher for any infinite field. So basically, the higher the dimension, the less restriction on the field you have to make abstractions to this Gromov cancellation by making the group non-zero. Yeah, so kind of to summarize this, one can say that in high dimension, all these groups are typically non-zero. Yeah, there's some technical assumptions, but probably one can push it to more general fields here and here. This is a bit different. We do need a small field to make some elliptic torsors appear. But these two cases are quite general and probably work even without these assumptions. So this is one way to formulate the main result, and I'll be explaining how to reformulate it and also what kind of geometry goes into proving this. So we'll be studying in a second not quite birationality of varieties, but birational maps, and we'll be looking at invariants of birational maps to prove results like this. But before I go into that general direction, I'll make an explicit example. So maybe you're wondering what's the explicit counterexample. So you may or may not like it. So kind of it's a little bit technical, but I'll give you an example. So it works over a field of characteristics 0, and I'm claiming that, so I'm looking at threefolds in P4. So there will be no equations, but I'll be explaining properties of two hypersurfaces. So varieties of dimension 3, both singular in P4, and how they violate Gromov cancellation. The first thing is that my W is P4 and the complements are actually isomorphic. The second thing is that there's some specific shape of these divisors, so they're both birational to P1 bundle of a certain surface, S or S prime, and there's something called K3 surfaces, both of them. So these surfaces are similar but different. Specifically, K3 surfaces are not isomorphic or not birational, but they are so-called derived equivalent. So motivically, they are closely related to each other, but they are not birational. And then an easy formal argument shows that in this case, these P1 bundles also cannot be birational. So kind of these 3 points is an example of a negative answer to Gromov cancellation, because we have complements which are the same, big variety which is the same, but the divisors, so hypersurfaces we remove, are not birational. So hence, in particular, you cannot make one into the other by cut and paste relations. So yeah, it looks a bit mysterious. So it comes from the following situation. So now this is where birational types meet birational maps. So it comes from a construction of Hassett-Lie, which did it over complex numbers, and then we extended it with Lin over any field of characteristic 0. That there's a certain, like this D and E appear as exceptional divisors of a certain birational map. So specifically, this side blows up one K3 surface, this side blows up another K3 surface, and this map contracts one divisor, this map contracts the other divisor. So somehow, the way to get these situations is to consider this birational map, which one way blows up one surface, the other way blows up another surface, and the surfaces are not birational to each other. Yeah, so this kind of the first counterexample to various things. So it implies Gromov's question is here, and also the first, this Gromov subgroup is non-trivial on this level. So when we do iota 3, we go from 3 folds to 4 folds. So we had 2 3-folds, which become the same on level 4, but are not the same on level 3. So that's the kind of how it works. Yes, and I earlier said that L is a 0 divisor, and interestingly, it's the same geometry which shows up to show that L is a 0 divisor. So basically, you get that L times one K3 minus another K3 is 0. So as an exercise using this, you also get this. That's not the first example, but that's how examples are typically obtained. Right, so basically what I want to do now, I want to study maps more systematically. To understand this Gromov's question, Gromov subgroups, I want to set up some machinery for invariance of birational maps to have a more flexible way of talking about these kind of things. Yeah, and that's what we call motivic invariance of birational maps. It's how our paper with Lin is called. Motivic invariance will mean taking values in one of the truncated Grothendieck groups, and birational maps are birational maps. Yeah, so what do I want to do? I want to have a machine which takes a birational map from X to Y. It could be X to X, but it's more natural categorically to do from X to Y, and then we allow compositions. But it could be just bir X, so the group of self-maps of X as well. But for all X and Y, we have this assignment into varieties of dimension up to n-1, and it's very important that my source varieties are dimension n, the same, and the target of this measures what happens at infinity at level n-1. Yeah, so the properties are as follows. So we kind of want to measure what this map here adds and removes with respect to X and Y. And one way to say this is as follows. For any open subset, you want to look at the complement at infinity. So you just declare that the invariant of an open inclusion, which is a very good example of a birational map, is just what you have added to U to make X. And why is it sufficient? Because the second property is that you want to be additive for compositions. So that's for every pair of composable maps from X to Y and then in Y to Z, you can compute the invariant of composition, and it should be equal to this invariant in this abelian group. Right, so what are some points here? So in very fancy language, it's a homomorphism from a groupoid to a group, right? So you have a groupoid of birational maps as a source, and the group here and the homomorphism is this property. Just you compose when you can, not always. And then another thing to state about this is that obviously 1 and 2 make a unique invariance. So this uniqueness here is obvious from the definition because every birational map will be decomposed into maps like this and their inverses. Therefore, if you know what to do for an open embedding and you know what to do for compositions, you sort of are forced to do certain things for everyone else. And what takes some work, even though it's a formal statement, one needs to prove why that natural thing is well defined. That if you look at, so I explained uniqueness, that it follows easily. In existence, you'd have to take a birational map, find common U in X and Y, take the differences of these guys, and then show that it's well defined. And then it's a homomorphism. So this is not very difficult, but it's a convenient formulation to have and to use. Yeah, so this C stands for centers. We kind of meant that center which is blown up or removed is something which this invariant records. Okay, so let's compare this with original formulation of the Gromov's question. So yeah, if you remember in Gromov's question, we had two embeddings of different varieties in the same W, and I want to make a birational map out of this situation. Birational map was this. The complements were isomorphic. This was an open embedding, which was a birational map. This is a bit strange. It's like it's an inverse to an open embedding, but it's actually a birational map. So kind of we work on the groupoid, and we can just say that, okay, it's not defined on X, and outside of X, it's identity. So that works. Right, so we set up a map from W to itself just by declaring what it does on the complement. Right, and then if we compute the invariant of this map, then just by definition, we have to take this plus, this is nothing, plus this. So we take plus y at this stage is here, and then minus x at this stage is here. Right, so kind of what I'm saying is that original Gromov's question is about the following. If you have a birational self-map from W to W, is the invariant 0 or not? That's kind of one way to understand it. Instead of saying these explicit things about cancellations or cut and paste, you want to know whether this class was actually already 0 at this level or it wasn't 0 at this level. Yeah, and as I'm saying, like, it's important that dimension of these guys is n, and here it's n minus 1, because of course on level n, this will become 0. Right, so if I start doing this, if I'm allowing myself computing this on level n, then this difference is 0. But we're measuring it on the previous level, n minus 1. And then it can be 0 or non-0. Right, so yeah, I want to make a more, now a relationship between what I called Gromov subgroups earlier and these invariants. And that's kind of a neat formula which relates the two. So let's see. So this is a formal statement, so it works, always works for any field and for any n where this makes sense. So on the left-hand side is what I call Gromov subgroups. That's the kernel of when you go from level n minus 1 to level n. The right-hand side is an infinite sum over all birational types of n-dimensional varieties. And here we compute the invariant of bir of x. So that now goes from x to x, a bit like here. Yeah, and kind of, yeah, there are two ways. Okay, so the formula says that all the non-cancellation issue actually are coming from birational self-maps. So the example here, or the example I gave earlier with P4, is the universal thing we have to consider. So in practice, we would put maybe simplest variety like P3, P4, and so on, but the formula says we have to look at all these x's. Yeah, so let's see why this is true. As usual, one of the inclusions is easy and the other takes some work. So the easy inclusion is that the right-hand side is contained in that kernel. And this is what I was saying here, that if you have a birational self-map, and then if you push this value to level n, by cancellation you get 0 on level n. So this is why everything which can possibly appear here is always in the kernel. What's a little bit more interesting is why all these kernels can be separated like that as self-maps, and it takes a little bit work, not too much work. It's, yeah, it's a relatively straightforward thing. I want to now reformulate what I said earlier about non-vanishing in these terms, and because this is how it's going to be proved. Yeah, but kind of I want to emphasize change of perspective here. So here we care about birational types, and here we care about birational maps. And depending on what we want to do, we can do either. But from now, I'll do birational maps. Yeah, and the non-vanishing from earlier can be interpreted as follows. So the invariant is non-zero in the cases I mentioned. Specifically, now there's a shift in n because now we'll look at, P3, P4, P5. Right, so basically the same assumptions as before, but now I'm explaining why those groups were non-vanishing. So it's because we are about to see some maps where the motivic invariant is not vanishing. And at this point, I am free to choose which varieties I work with, and Pn is the relevant one, which carry a lot of interesting maps for my non-vanishing. Even though in principle there could be other varieties. Yeah, we have a theorem which is more general, which puts some more general varieties here with properties. Yeah, so the picture of the proof is what I had earlier. So we need to construct interesting self-maps from Pn to Pn under these assumptions, which blow up kind of one thing here, which adds to your invariant, and blow down another thing here, which remove from your invariant. And it's based on work of other people, such as for fourfolds, that's a Hassett-Lie link I already mentioned. Then for P5 it's Itomuro, Kabu-Uedo, and for P3 it's my joint work with Zhang. Yeah, so that's the basic idea. We need to generate some interesting maps. And I said I will mention something about why these fields. So like why, for example, this function field or number field. What's special about those cases? Note that there's something we don't know, right? So complex numbers here, we don't, yeah, so it's a bit different. Yeah, so I want to give you some more details about the construction. So I said we want to make a blow up and a blow down, and specifically, yeah, let's think what kind of things will be blowing up and blowing down. Right, so the smallest dimensional case where this can ever exist, because I explained that for P2 there will be nothing, for surfaces there will be nothing, but P3 is the first situation where we can have something. And then it's quite restrictive what kind of things we can do, and the example is elliptic curves. Elliptic curves, which are twisted forms of one another, yeah, this is why we need a small field where such twisted forms will exist. Every such link that is presented here, so link is blow up, blow down, will necessarily give a trivial invariant over algebraic closure because the centers become isomorphic over the algebraic closure. However, over fields as I list here, there exist such torsors, and there's an explicit construction originating from a Mori-Mukai link between P3 and the quadric, which, yeah, so basically, how are we supposed to get the second Jacobian of a genus 1 curve? The basic thing is that we'll be blowing up a certain genus 1 curve, and we'll be contracting the secant lines to that curve. And the secant lines, so the lines intersecting that curve twice, will contract not onto the original curve Z, but onto the second Jacobian Pic2Z. So first to symmetric square, and then to the second Jacobian. So it's like a subtle arithmetic thing, and it's a pleasant thing to prove something and compute some classes in the Tate-Shafrevich group. Okay, so this was the smallest dimensional case, but necessarily not algebraically closed. So algebraically closed, yes, so for P3 they wouldn't exist. So in larger dimensions, yeah, it will be different. So it won't be curves, but they'll be more geometric. So this were this derived equivalent K3 surfaces of degree 12 that I mentioned already. So that counterexample to Gromov's question, which I gave earlier, involves some map from P4 to P4, and there were some exceptional divisors, and there were two K3s which were blowing up on the two sides in the Hassett-Lie map. Yeah, and finally, in this constructions, the n equals 5 is for any field. You look at certain Calabi-Yau threefolds sitting inside P5, and this was constructed by Itomura, Kawa, and Ueda. And again, they did yeah, so they did the theorem over complex numbers and we extended it to any field. So I'm explaining this dimension 3, 4, 5 because you can then spread this out by multiplying by P1. There's a cheap process how you can make higher dimensional examples by multiplying everyone by P1 and keeping the birational types of the centers. So basically just formally, as soon as you can make a 5 here, you can make everything bigger just by taking this map times every object by P1. Motivic invariant will multiply by P1 and it still will be non-zero because, yeah, there's some reason for why these guys are not stably birational. Yeah, so, right, so I mentioned this word earlier, derived equivalence. So in these examples, Z and Z prime are not birational and it's important for our applications, but they happen to be derived equivalent in each situation. So they motivically are very close. So technically derived categories of coherent sheaves are equivalent. And yeah, it wasn't clear for us for quite some time, but the way I see it now is that it has to do with conjectural canonical decompositions of derived categories into something called atoms. Yeah, so if a certain, yeah, so basically conjecturally the center is derived equivalence and it follows from a certain expectation about how derived categories should decompose. And actually on Tuesdays, I have some lectures here about atomic decompositions in dimension 2. But that's not what I'll talk about. Yeah, so there's some references for this atomic decomposition. So Kontsevich, Katsarkov, Pantsev, and Hu did something called Hodge atoms, which is quantum homology device giving abstractions to rationality. Halpern-Leistner provides some conjectural framework for these atomic decompositions, and I have a joint work with Bldg and Schneider where we do atomic decompositions for surfaces. So basically, if these decompositions exist, then maybe there can be non-cancellation birationally, but there's a complete cancellation on the level of derived categories. This is the logic. In particular, for Calabi-Yao's, derived categories should match up perfectly. So, yeah, this was what I want to say about Gromov's question and how how constructions apply. Now I want to explain what kind of results what I said gives for the structure of the Cremona groups. So as a consequences of existence of this invariance and on vanishing of this invariance, we get some new applications to the study of these big and complicated groups, birational maps of Pn. These are very big infinite dimensional groups. Right, so yeah, so I'm looking at P4 and higher, where it was the Hassett-Leiling. And yeah, so I want to emphasize some group theoretic properties of these groups and how this follows from what we do. So typically one wants to know what these Cremona groups are generated by or not generated by. And for example, whether they're generated by involutions or more generally elements of finite order. But like our invariant provides a homomorphism from Cremona group to some abelian groups. And even though those abelian groups are not free, as I said, we can single out a homomorphism to a free abelian group by the constructions that I presented. If we start varying the objects in moduli, we get infinitely many so uncountably many homomorphisms to Z, which make up a homomorphism such group, which necessarily factors through the abelianization. And contains a direct summand is just because this surjection will split. So that's kind of one sort of properties, yeah, and so not generated in particular by involutions or finite order elements. And like another thing people kind of were asking in this domain is about regularizable elements. So are we generated by certain specific kinds of elements, which I'll now briefly define and show how this goes. Yeah, so a regularizable element is a particular simpler type of elements in birational automorphism group is the one conjugate to an actual automorphism. So in this kind of situation where we have automorphisms and birational automorphisms, there are some better birational automorphisms which have a model on which they act regularly, right? So I want to I look at my birational map of Pn and I want to conjugate it to put it on some other target where it's an automorphism. And in principle, it's not clear one way or the other from definitions whether maybe every birational automorphism has such a property. And notably, there's a Weyl regularization theorem that elements of finite order actually are regularizable. One can construct a model on which they act regularly. However, it was known for a while that not every element is regularizable, but it wasn't known whether regularizable ones generate or not, as there are a lot of them, obviously. So hence here in the statement, yeah, I said finite are regularizable, hence the question is just about regularizable before finite is already included here. Yeah, and that's a kind of a very neat proof that I want to finish with. Right, so let's see. Once we have set up the machinery, we just easily see that if we're conjugating in our groupoid, the output doesn't change. So because the target is an abelian group, this conjugation here is canceling. So it's just a question about this. So the issue is about whether automorphism has zero invariant, and of course automorphism has zero invariant by definition. Therefore, everyone conjugate to automorphism also has zero invariant. Therefore, the whole normal subgroup generated by this regularizable guys, you get a zero map. So if you were generated by regularizable, it would force motivic invariance to be zero. And this is true for P2, where it's generated by evolutions by the Noether-Kosterlitz theorem, and indeed then the invariant is zero. However, this shows that for P4 and higher, in this over basically almost all fields, or for 3 and higher over small fields, it's not generated by elements like this. Okay, so these were the two properties of the Cremona groups, which we can deduce using the technology we have. And so I think I'll just summarize what I was talking about. Yeah, right, so kind of, that's not how we said it in the paper, but this talk I focused around Gromov cancellation question, which asked whether open embeddings are isomorphic, implies that x and y are birational. And at the time it was asked, very little was known, only the positive directions, but now it's clear that it's often negative, fully controlled by the structure of the truncated Grothendieck groups and there's Gromov subgroups. Right, and then we reformulated this in terms of motivic invariant of birational maps, which allowed some more flexible language to talk about this phenomena, and also gave new applications to the birational groups of various varieties, such as higher dimensional projective spaces. Yeah, and one thing which we don't know, but maybe we'll find out at some point, is that what about derived categories and derived equivalence? So conjecture there's something there, but we don't know how to prove it yet. Yeah, thank you, that's all.